In 1900, in a lecture hall at the Sorbonne in Paris, a 68-year-old German mathematician named David Hilbert stood in front of the most accomplished mathematicians on the planet and made a promise. He told them that every mathematical question has an answer, that there is no problem in mathematics that cannot eventually be solved. He said this with such confidence that it became the defining ambition of an entire generation of mathematicians. And for 30 years, the smartest people alive worked to prove him right. They failed, completely and irreversibly. What they found instead is something you were almost certainly never taught in school. And it is something that the scientific establishment has spent the better part of a century trying not to think too hard about. In 1931, a 25-year-old Austrian logician named Kurt Gödel proved that mathematics contains true statements that can never be proved. 5 years later, a 24-year-old Englishman named Alan Turing proved that there is no general procedure, no algorithm, no machine of any kind that can determine whether an arbitrary mathematical statement is true or false. And in 2015, a paper published in Nature proved that these results are not just abstract curiosities confined to the blackboards of logicians. They reach down into the physical structure of matter itself. There are properties of real materials, things you could hold in your hand, that are mathematically undecidable, not hard to determine, not beyond current technology. Undecidable, meaning no amount of mathematical progress, no future theory of everything, no axiom system anyone will ever devise can answer these questions. And nobody told you. You went through school, maybe through university, and you were given the impression that mathematics is the one domain where certainty exists, that unlike history or politics or psychology, mathematics deals in proof, in absolute truth. You were told that if something is true, it can be proved, and if it cannot be proved, it is not really true, just a conjecture waiting for a cleverer mathematician. That impression is wrong. It was proved wrong in 1931, and the proof has only gotten worse in the 95 years since. Much worse. That is what this is about. Not just the theorems, although we will go through them in detail, because they are among the most beautiful and terrifying results in the history of human thought. This is about what it means that mathematics, the one tool we trusted to describe reality completely, has been proved to have permanent holes in it, gaps that cannot be filled. And it is about what happened to the two men who discovered those holes, because both of them were destroyed. One starved himself to death at the age of 71 because his paranoia became a closed loop he could not escape. The other was chemically castrated by the government of the country he had personally saved from Nazi Germany and was dead of cyanide poisoning at 41. The math that proved the limits of knowledge could not protect the people who found those limits. But we need to start at the beginning. We need to start with the promise. David Hilbert was born on January 23, 1862, in Königsberg, Prussia. By the turn of the 20th century, he had transformed the University of Göttingen into the undisputed mathematical capital of the world, and he had done something no other mathematician of his era managed. He had made pure mathematics feel like a moral mission. When he stood in Paris on August 8, 1900, and posed 23 unsolved problems to the international mathematical community, he opened with a question that sounds almost naive now. Who of us would not be glad to lift the veil behind which the future lies hidden? But it was not naive. It was a battle cry. Hilbert believed, with a conviction that bordered on religious faith, that there would be no ignorableness in mathematics. No, we shall not know. Every question had an answer. Every answer was reachable. The only limit was time and effort. This crystallized in the 1920s into what became known as Hilbert's Program. The goal was to prove three things about mathematics. First, that it was complete, meaning every true statement is provable. Second, that it was consistent, meaning no contradictions can arise. And third, that it was decidable, meaning there exists an algorithm, a mechanical procedure that can determine the truth or falsity of any mathematical statement. That third question had a name, the Entscheidungsproblem, the decision problem. Hilbert and his colleague Wilhelm Ackermann posed it formally in their 1928 textbook, and Hilbert called it the main problem of mathematical logic. Think about what he was claiming. He was saying that mathematics is a closed system, that if something is true, you can prove it, that if you want to know whether a statement about numbers is correct, there exists a procedure, something you could in principle build a machine to carry out, that will give you the answer every time, for any question. That is not just a technical claim about logic. That is a claim about the nature of reality. Because if mathematics is complete and decidable, then the universe, to the extent that it is described by mathematical laws, is fully knowable. There are no permanent mysteries, only temporary ignorance. This was not just Hilbert's private belief. It was the operating assumption of an entire era. The early 20th century was the age of foundations. Russell and Whitehead were building mathematics from logic. Hilbert was trying to prove it secure. Zermelo and Frankel were axiomatizing set theory. The program was to put all of mathematics on a footing so solid that no paradox, no inconsistency, no gap could ever appear. The assumption was that this was possible, that the only question was how to do it, not whether it could be done. And the confidence behind this assumption was not idle speculation. It was backed by centuries of mathematical success. Every problem that had been posed had eventually been solved. The track record was perfect. Of course, mathematics was complete. How could it not be? The foundations for this dream had been laid by Bertrand Russell and Alfred North Whitehead in a work called Principia Mathematica, published in 3 volumes between 1910 and 1913. This was an attempt to derive all of mathematics from pure logic, to build the entire edifice of mathematical truth on a foundation of logical axioms so simple and so obviously correct that no reasonable person could doubt them. The most famous result in the entire work is the proof that 1 + 1 = 2. It takes approximately 360 pages of preliminary definitions and appears as theorem star 54.43 on page 379 of Volume 1, accompanied by the driest footnote in the history of publishing. From this proposition, it will follow, when arithmetical addition has been defined, that 1 + 1 = 2. The full proof wraps up on page 86 of Volume 2, with the remark, "The above proposition is occasionally useful." Russell had been driven to this project by something deeply unsettling. In 1901, he had discovered a paradox that cracked the foundations of set theory. Consider the set of all sets that do not contain themselves. Does it contain itself? If it does, then by definition it should not. If it does not, then by definition it should. There is no consistent answer. The paradox is simple enough for a child to understand, and it destroyed the foundations of mathematics. He wrote to the German logician Gottlob Frege on June 16, 1902, to inform him of this paradox, and the timing could not have been worse. Frege was in the process of publishing his life's work on the logical foundations of arithmetic. The paradox demolished it. Frege was devastated. Russell's Principia attempted to patch the hole with an elaborate system of hierarchical types that prevented self-reference, but the system required axioms: the axiom of infinity, the axiom of choice, the axiom of reducibility, that were not themselves provable from logic. The pure logicist dream was compromised from the start. But Hilbert was undeterred. He pressed forward. At the 1928 Bologna Congress of Mathematicians, he explicitly asked the community whether mathematics is complete, consistent, and decidable. He was 66 years old and suffering from pernicious anemia, but his intellectual ambition had not dimmed at all. He would retire 2 years later, and on the occasion of his retirement, he would say something that became the most ironically timed sentence in the history of science. On September 8, 1930, Hilbert delivered his retirement address to the Society of German Scientists and Physicians in the city of Königsberg. He concluded with 6 words that would be carved on his tombstone: "Wir müssen wissen." We must know. We will know. A 4-minute excerpt was broadcast by radio, one of the earliest audio recordings of a major mathematician. The confidence in his voice is absolute. He had no idea what was about to happen, because the day before, September 7th, 1930, in the same city, at a small academic conference that Hilbert did not attend, a 24-year-old logician from Vienna had quietly announced that the dream was dead. The 24-year-old's name was Kurt Gödel, and what he had found was not a limitation that could be patched or worked around. It was a proof that the limitation is permanent, structural, and built into the nature of mathematics itself, not a wall that future mathematicians might scale, a theorem that says the wall is infinite. And that result, disturbing as it was, turned out to be just the beginning, because what Godel found inside mathematics, a man named Alan Turing would find inside computation. And what Turing found inside computation, physicists in the 21st century would find inside physical matter itself. The limits are not abstract. They are not metaphorical. They are woven into the fabric of reality. And the thread that connects all of it has been sitting in plain sight for almost a century, published in the most prestigious journals on earth, and almost nobody outside of a handful of specialists has been told what it actually means. The conference where Godel made his announcement was called the Second Conference on the Epistemology of the Exact Sciences. It ran from September 5th through 7th, 1930, in Königsberg. The headliners were impressive. John von Neumann, who was 26 and already considered one of the most brilliant mathematicians alive, gave a 1-hour address on formalism. Rudolf Carnap spoke on logicism. Arndt Halting represented intuitionism. These were the 3 great schools of mathematical philosophy, and each was making its case for how to understand the foundations of mathematics. On the 3rd day, during a roundtable discussion, Godel, who was 24 years old and had published almost nothing, mentioned in passing that he had constructed true mathematical statements that could not be proved within any consistent formal system strong enough to express basic arithmetic. Almost nobody reacted. The remark was brief. The implications were so enormous that the audience essentially could not hear what he was saying. It was like someone casually mentioning at a dinner party that they had discovered the Earth was going to be hit by an asteroid. The claim is so large that the brain files it as a mistake and moves on. But one person in the room understood immediately. Von Neumann pulled Godel aside after the session and asked him to explain in detail. Within weeks, working independently, von Neumann had derived the second of Gödel's two incompleteness theorems on his own. He wrote to Godel on November 20th, 1930, to share his result, only to learn that Godel had already submitted a paper containing the same theorem 3 days earlier. Von Neumann's response was extraordinary. He dropped his own work entirely and ceded priority without hesitation, writing on November 29th, "As you have established the theorem on the unprovability of consistency as a natural continuation and deepening of your earlier results, I clearly won't publish on this subject." He later called Godel the greatest logician since Aristotle and described his achievement as singular and monumental. Indeed, it is more than a monument. It is a landmark which will remain visible far in space and time. When von Neumann was lecturing on Hilbert's program at Princeton and read Godel's paper, he cancelled the rest of the course and spent the remaining lectures explaining what Godel had done instead. So, what had Godel actually proved? Kurt Friedrich Gödel was born on April 28, 1906, in Brunn, Austria-Hungary, now Brno in the Czech Republic. His family was prosperous. His father ran a textile factory. As a child, he was nicknamed Der Herr Warum, which translates to Mr. Y, because he never stopped asking questions. He enrolled at the University of Vienna in 1924, originally intending to study physics, but lectures on number theory by Philipp Furtwängler converted him to mathematics. His doctoral advisor was Hans Hahn, one of the leaders of the Vienna Circle, the intellectual headquarters of logical positivism, the philosophy that held that meaningful statements must be empirically verifiable and that metaphysics is nonsense. Godel attended the Vienna Circle's meetings starting around 1926, but his own philosophical views were the exact opposite of everything the Circle believed. He was a committed Platonist. He believed mathematical objects exist in an abstract realm independent of human minds, independent of physical reality, independent of whether anyone ever discovers them. Russell would later write, with a note of bewilderment, that Godel turned out to be an unadulterated Platonist and apparently believed that an eternal knot was laid up in heaven, where virtuous logicians might hope to meet it hereafter. In 1929, Godel completed a doctoral dissertation proving the completeness of first-order logic. This seemed like great news for Hilbert. It showed that, in a restricted but important domain, every logically valid statement could be proved. But Godel was already working on something else, something that would demolish the program from the inside. His paper was titled On Formally Undecidable Propositions of Principia Mathematica and Related Systems, Part 1. It was submitted to the journal Monatshefte für Mathematik und Physik on November 17, 1930, and published in 1931, volume 38, pages 173 through 198. He was 25 years old. The part 1 in the title promised a sequel. It was never written. Part 1 was devastating enough. The method was breathtakingly original. Godel invented a technique now called Godel numbering. He assigned a unique natural number to every symbol, every formula, and every sequence of formulas in a formal system. Each mathematical statement became a number. Each proof became a number. The system could now make statements about its own statements, because statements about numbers were statements the system was designed to handle. He had found a way to make mathematics look at itself. The key insight was a twist on the liar's paradox. The sentence, "This statement is false," creates a contradiction, and logicians had known for centuries to stay away from it. But the sentence, "This statement is not provable," does something different. It does not create a contradiction. It creates incompleteness. Godel constructed a formal sentence, now called the Godel sentence, that effectively says the formula with Godel number G cannot be proved in this system. If G is provable, then the system has proved something false, which means the system is inconsistent. If G is not provable, then the statement is true because it correctly asserts its own unprovability. Either way, the system is broken. Either it proves false things or it fails to prove true things. You can have consistency or you can have completeness. You cannot have both. That was the first incompleteness theorem. Any consistent formal system capable of expressing basic arithmetic contains true statements that are unprovable within the system. The second incompleteness theorem was even worse. No such system can prove its own consistency. If it could prove itself consistent, it would actually be inconsistent, because Godel showed that the statement, "This system is consistent," is one of the unprovable true statements. The system cannot verify its own foundation. Think about what this means. It means there are mathematical truths, real, actual truths about numbers that will never be proved from any finite set of axioms. Not because we have not found the right axioms yet, because no set of axioms is sufficient. Add new axioms and new unprovable truths appear. The gap can never be closed. It is structural. It is permanent. It is a feature of any system rich enough to talk about basic arithmetic. And basic arithmetic is not exotic. It is the mathematics of counting, the mathematics that describes discrete quantities, the mathematics that underlies every calculation your computer has ever performed. The incompleteness is not in some remote corner of abstract algebra. It is at the foundation. There is something else about Godel's result that rarely gets mentioned. His 1929 dissertation had proved the completeness of first-order logic. Completeness. The year before his incompleteness result, he had proved the opposite thing for a simpler system, which means he knew exactly what was at stake. He understood Hilbert's dream from the inside. He had contributed to it. And then he proved it was impossible. It was not an outsider's attack. It was a demolition from within. Now, here is the part that should unsettle you. When Godel announced this result, Hilbert's reaction was almost non-existent. He never publicly conceded that his program was dead. He addressed Gödelian issues in 2 papers published in 1931 without mentioning Gödel by name, and continued pursuing modified approaches until his health deteriorated. His collaborator Paul Bernays understood immediately, and privately, von Neumann was telling people that Godel had ended the dream. He wrote to Carnap in June 1931, Godel has shown the unrealizability of Hilbert's program. There is no rigorous justification for classical mathematics, but the man whose dream had been destroyed never acknowledged it publicly. And Russell, the man who had spent a decade of his life writing 3 volumes of Principia Mathematica specifically to put mathematics on secure logical foundations, in a 1963 letter to the logician Leon Henkin, Russell seemed to suggest that Gödel's theorems meant 2 + 2 = 4.001 was permissible. Historian Ivor Grattan Guinness interpreted this as evidence that Russell never fully understood the theorems, even 3 decades after they were published. The man whose life's work had been most directly demolished by the result apparently never grasped what it meant. There is a story about Godel that seems almost too perfect to be true, but it is documented by Oscar Morgenstern, who was there. On December 5, 1947, Godel went to take his United States citizenship exam. While preparing, he had studied the American Constitution with his characteristic obsessive intensity and claimed to have discovered what he called an inner contradiction, a way the Constitution could legally be used to establish a dictatorship. What he probably found involves Article 5, which allows the Constitution to amend itself, which means it could, in theory, amend itself into non-existence. Both Morgenstern and Einstein, who accompanied Godel to the exam, were horrified and begged him not to bring this up. At the exam, Judge Philipp Foreman asked Godel what kind of government Austria had. It was a republic, Godel replied, but the constitution was such that it finally was changed into a dictatorship. Oh, this could not happen in this country, the judge said, reassuringly. Oh yes, I can prove it, Godel answered. Einstein and Morgenstern exchanged panicked looks. The judge mercifully moved the conversation along. Godel received his citizenship. The man who proved that systems contain their own contradictions found a constitutional loophole that proved the same thing about American democracy. He could not help himself. He saw self-reference everywhere, because it was everywhere. That was his gift, and eventually his curse. That should bother you. The people who should have been the most alarmed, who should have been on the front pages of every newspaper in the world, explaining that mathematics itself had been proved permanently, either did not understand, did not care, or chose not to talk about it. And that pattern of institutional silence did not end in 1931. It continued through the next result, which was worse, and through the result after that, which was worse still, because Godel had shown that formal systems have permanent gaps, but formal systems are just one way of trying to capture truth. What about computation? What about building a machine, a procedure, an algorithm that could mechanically decide whether mathematical statements are true or false? Hilbert's Entscheidungsproblem was still technically open. Maybe you could not prove everything, but maybe you could at least build a machine that could decide everything. You cannot, and the person who proved it was a 24-year-old Englishman who reportedly had the idea while lying in the grass in a meadow outside Cambridge. Alan Turing was born on June 23, 1912, in Paddington, London. His father, Julius, worked in the Indian Civil Service. His mother, Ethel, was the daughter of the chief engineer of the Madras Railways. Both parents were frequently in India, and young Alan was left with foster families in England for long stretches of his childhood, which may explain the quality of self-contained intensity that characterized him his entire life. At Sherborne School, which he entered in 1926, Turing was brilliant and almost comically undisciplined. His headmaster complained that if he is to stay at public school, he must aim at becoming educated. If he is to be solely a scientific specialist, he is wasting his time. He read Einstein's work and Eddington's The Nature of the Physical World before he had studied elementary calculus. He formed a deep bond with another student named Christopher Morcom, believed by biographers to be his first love. Morcom died of tuberculosis on February 13th, 1930. Turing was 18. The loss shaped the rest of his life. In letters, he wrote about the possibility of surviving death, about whether the mind could exist independently of the body, about the nature of the soul. These were not idle musings. They were the questions that would, within a decade, lead him to formalize what computation is and what it cannot do. The death of the person he loved most drove him to ask whether minds are machines, and the answer he found changed the world. It may also have contributed to his atheism. He went to King's College, Cambridge, in 1931, graduated with distinction in 1934, and was elected a Fellow in 1935 at the age of 23. During lectures by M.H.A. Newman on the foundations of mathematics, Newman presented Hilbert's Entscheidungsproblem to the class, explaining that no one had yet proved it solvable or unsolvable. The story goes that Turing had the central idea of his most important paper while lying in the grass in Grantchester Meadows in the summer of 1935. He was 23 years old and about to invent the conceptual foundation of the modern computer as a side effect of solving a problem in mathematical logic. His paper was titled Uncomputable Numbers, with an application to the Entscheidungsproblem. It was received by the London Mathematical Society on May 28, 1936, and published in 2 parts on November 30th and December 23rd, 1936. In it, Turing did 2 things simultaneously. He invented an abstract model of computation, now called a Turing machine, and he used it to prove that Hilbert's decision problem is unsolvable. A Turing machine is not a physical machine. It is a thought experiment. Imagine an infinitely long tape divided into cells, each of which contains a symbol. A read/write head moves along the tape, one cell at a time. Based on the symbol it reads and its current internal state, it writes a new symbol, moves one cell left or right, and transitions to a new state. That is it. That is the entire device. And Turing proved that a single universal Turing machine, properly programmed, could simulate any other Turing machine. This is the theoretical foundation for the general-purpose programmable computer. Every laptop, every server, every phone you have ever used is a physical approximation of the abstract device Turing described in that paper. But the point of the paper was not the machine. The point was what the machine could not do. Turing proved that there is no algorithm, no Turing machine, no computational procedure of any kind that can determine, for every possible program and every possible input, whether that program will eventually stop running or continue running forever. This is the halting problem, and the proof is one of the most elegant arguments in mathematics. Assume, for the sake of contradiction, that such a machine exists. Call it H. H takes as input any program and its input, and correctly outputs, halts, or runs forever. Now construct a new machine P that does the following. P takes its own description as input and feeds it to H. If H says P halts, then P deliberately runs forever. If H says P runs forever, then P deliberately halts. What happens when you run P? If P halts, then H said it halts, which means P was supposed to run forever. If P runs forever, then H said it runs forever, which means P was supposed to halt. P halts if and only if it does not halt. That is a contradiction. Therefore, H cannot exist. Read that again. This has nothing to do with technical limitations. Nobody needs to build a faster computer or find a cleverer algorithm. The proof is a logical impossibility. No machine, no algorithm, no procedure of any kind in any universe with any laws of physics can solve the halting problem in general. The undecidability is absolute. And notice the structure of the proof. It is self-reference again, just like Russell's paradox, just like Gödel's sentence. The machine is asked about itself, and the question collapses into contradiction. Self-reference, the thing Russell tried to ban with his type theory, the thing Godel weaponized with his numbering system, keeps appearing because it is not a trick. It is a fundamental feature of any system rich enough to describe itself. You cannot build a system powerful enough to talk about everything without giving it the ability to talk about itself. And the moment it talks about itself, the limits appear. Every time, in every system, in every domain where it has been tested. And here is where it connects to Godel. If mathematics were complete, meaning every true statement were provable, you could solve the halting problem. For any program, you would just search through all possible proofs until you either found a proof that it halts or a proof that it runs forever. Since every true statement is provable, you would always find one. The search would always terminate. But Turing proved the halting problem is unsolvable. Therefore, mathematics cannot be complete. As computer scientist Scott Aronson later put it, once you have Turing's results, Gödel's results fall out for free as a bonus. Turing's result is, in a precise sense, deeper than Gödel's because it implies Gödel's theorem as a consequence. Now, there is a coincidence here that deserves attention. Just days before Turing submitted his paper, Newman received a copy of a paper by the American mathematician Alonzo Church, published in April 1936, that independently proved the Entscheidungs problem unsolvable using a completely different method called lambda calculus. Newman wrote to Church on May 31st, 1936, acknowledging what he called the rather painful overlap. But Church, who refereed Turing's paper for publication, recognized that the two approaches, while equivalent in their conclusions, were fundamentally different in their power. Turing's formulation had what Church called the advantage of making the identification with effectiveness in the ordinary, not explicitly defined sense, evident immediately. In other words, Turing had captured something Church had not. He had given the world a concrete, physical picture of what computation actually is: a machine, a tape, a set of rules. That picture was so convincing that even Godel, who had been skeptical of Church's lambda calculus as a definition of effective calculability, calling it thoroughly unsatisfactory, was immediately persuaded by Turing's analysis. Turing added an appendix to his paper, proving that his notion of computability was equivalent to Church's. Stephen Kleene formalized the connection in 1943 as the Church-Turing Thesis, which states that any function computable by any effective method is computable by a Turing machine. It is a thesis rather than a theorem because it equates an informal concept, effective calculability, with a precise mathematical definition. And informal concepts cannot be formally proved equivalent to anything. But the evidence is overwhelming. Every independently proposed model of computation, Turing machines, lambda calculus, recursive functions, register machines, cellular automata, even quantum computers, computes exactly the same class of functions. Nothing more, nothing less. Quantum computers, despite all the hype, do not break this barrier. They can solve certain problems faster than classical computers, but they cannot solve problems that classical computers cannot solve at all. The halting problem is just as unsolvable on a quantum computer as it is on your laptop. The consensus among computer scientists, formalized by Arrighi and Doeg in 2011, is that under reasonable physical postulates, the Church-Turing thesis holds even for quantum systems. There have been exotic proposals to circumvent it. Malamud-Hogarth spacetimes, where a computer could run for infinite subjective time within a finite objective interval. Xenomachines that perform infinitely many steps in finite time. None of them work. They all collapse under scrutiny, either violating known physics or introducing other impossibilities. If the Church-Turing thesis is correct, and virtually every computer scientist alive believes it is, then Turing's limits are not limits of a particular model. They are limits of computation itself. There is a person who deserves mention here and almost never gets it. Emile Leon Post, born February 11th, 1897, in Augusto, in the Russian Empire, independently developed a formal model of computation equivalent to Turing's, published in 1936. But that is not the remarkable part. During a postdoctoral year at Princeton in 1920 through 1921, Post had anticipated the work of both Godel and Turing on incompleteness and undecidability by a full decade. He had seen the shape of it. He knew what was coming, but severe manic depressive episodes requiring repeated hospitalization prevented him from publishing these ideas. Herman Weyl wrote to him sympathetically in 1942, "I have little doubt that 20 years ago your work, partly because of its revolutionary character, did not find its true recognition." Post died on April 21st, 1954, following electroshock therapy at the age of 57, the same year Turing died. Two men who saw the limits of what can be known, destroyed by systems that could not comprehend what they had found. But there is something worse than what happened to Post, because what happened to Turing was not just institutional indifference. It was institutional cruelty, and it was directed at the man who had personally done more to save Britain from Nazi Germany than almost any other individual alive. Turing went to Princeton in 1936 to study with Church. He earned his PhD in 1938 with a dissertation on systems of logic based on ordinals. John von Neumann was so impressed that he offered Turing a position as his assistant at $1,500 a year. Turing turned it down and went home to England. He had already been recruited by the Government Code and Cipher School, and on September 4th, 1939, one day after Britain declared war on Germany, he reported for duty at Bletchley Park. At Bletchley, Turing led Hut 8, the section responsible for cracking German naval Enigma. The Enigma machine used by the German military for encrypted communications, produced codes of such complexity that the Germans believed them unbreakable. They were wrong, and the reason they were wrong was substantially Turing. He designed the bomb, an electromechanical device fundamentally different from the earlier Polish bomber, incorporating a critical refinement called the diagonal board, devised by his colleague Gordon Welchman. The first bomb, codenamed Victory, was installed on March 14, 1940. By the end of the war, 211 bomb machines, operated by approximately 1,676 female members of the Women's Royal Naval Service, were decrypting up to 84,000 Enigma messages per month. 2 messages every minute, around the clock, every day. Bletchley Park grew from roughly 200 staff at the war's start to some 10,000 by 1944. Historians estimate the codebreakers' work shortened the war by approximately 2 years and saved an estimated 14 million lives. 14 million lives. That is not an abstraction. Those are people who drew breath, raised children, grew old because of work done by a mathematician in a wooden hut in the English countryside, and the work was classified. Nobody could know. For decades after the war, the people who had worked at Bletchley Park could not tell anyone what they had done or why it mattered. The government classified the entire operation and kept it classified until the mid-1970s, which meant that when the British state turned on Turing, the public had no way of knowing what they were watching. They were watching a nation prosecute one of the men most directly responsible for its continued existence, and they could not even be told why that sentence should horrify them. After the war, Turing worked on the automatic computing engine at the National Physical Laboratory, then moved to Manchester University. In October 1950, he published Computing Machinery and Intelligence in the journal Mind, proposing what became known as the Turing test. If an interrogator communicating via text cannot reliably distinguish a machine from a human, the machine exhibits intelligence. And in that same paper, he directly addressed the Gödelian objection to machine intelligence. The argument goes that Gödel's theorems prove machines cannot think because a human can always see the truth of a Gödel sentence that the machine cannot prove. Turing's response was precise and prescient. A human could triumph over any particular machine, but it would be impossible to triumph over all machines simultaneously. The objection, he said, does not establish what it claims. In August 1952, the Philosophical Transactions of the Royal Society published his paper, The Chemical Basis of Morphogenesis, his only biology paper, and arguably his most prophetic. He proposed that chemicals he called morphogens, reacting together and diffusing through tissue at different rates, could explain how a symmetric embryo develops asymmetric structures, spots, stripes, waves, the patterns on a zebrafish, the spacing of hair follicles, the ridges on the roof of your mouth. The paper was ignored for 25 years, overshadowed by the discovery of DNA structure in 1953. Modern biology has vindicated it spectacularly. Turing patterns have been confirmed in hair follicle distribution in mice, digit patterning in vertebrate limbs, mollusk shell markings, and in 2021, Turing patterns were observed at the atomic scale. He wrote that paper while undergoing chemical castration. In December 1951, Turing had met Arnold Murray, a 19-year-old unemployed man on Manchester's Oxford Street. When Turing's house was burgled in January 1952 by an acquaintance of Murray's, he reported it to police and during questioning admitted to the relationship. Both were charged under the Labouchere Amendment, the same statute that had been used to prosecute Oscar Wilde 57 years earlier. On March 31st, 1952, Turing pleaded guilty and was sentenced to 12 months probation, conditional on undergoing chemical castration, injections of diethylstilbestrol, a synthetic estrogen, for 1 year. The treatment caused impotence, weight gain, and breast tissue growth. Turing wrote, with the kind of dark understatement that characterized him, "It is supposed to reduce sexual urge whilst it goes on, but one is supposed to return to normal when it is over. I hope they're right." His security clearance was revoked. He was barred from cryptographic work. He was also barred from traveling to the United States, where much of the cutting-edge work on computing was happening. The man who had invented the theoretical foundation of the computer, who had personally saved millions of lives through applied mathematics, was now considered a security risk because of who he loved. Meanwhile, his morphogenesis paper, one of the most original pieces of theoretical biology ever written, was being published by the Royal Society. He was simultaneously producing work of historic importance and being dismantled by the state. The two things were happening at the same time to the same person, and nobody in a position of authority saw the contradiction. On June 7th, 1954, Turing was found dead in his bed at his home in Wilmslow, Cheshire. He was 41 years old. The cause of death was cyanide poisoning. A half-eaten apple lay beside his bed. The apple was never tested for cyanide. A jar of cyanide solution related to an electroplating hobby was found in his spare room. The coroner ruled suicide. The verdict has been challenged. Turing's friend Peter Hilton described his response to the entire legal ordeal as one of amused fortitude. He had left a to-do list on his desk for the following week. Philosopher Jack Copeland argues the evidence would not sustain a suicide verdict today. Turing's mother Sarah never accepted it, maintaining it was an accident caused by careless storage of chemicals. His biographer Andrew Hodges speculated he was reenacting a scene from Snow White and the Seven Dwarfs, his favorite fairy tale, the scene where the Wicked Queen immerses her apple in the poisonous brew. On December 24, 2013, Queen Elizabeth signed a posthumous royal pardon. It was only the fourth such pardon since the end of the Second World War. The Alan Turing law, part of the Policing and Crime Act of 2017, extended posthumous pardons to approximately 49,000 men convicted under historical anti-homosexuality statutes. On June 23, 2021, Turing's birthday, the Bank of England released a £50 note bearing his portrait. 67 years, that is how long it took for the country he saved to put his face on its currency instead of a criminal record in its files. And the other man who mapped the limits of knowledge, his end was, if anything, even more deeply disturbing, because it was not imposed from outside. It came from within. After the Anschluss of March 12, 1938, Godel found himself in a dangerous position in Vienna. Though not Jewish, he was closely associated with Jewish intellectuals and had been attacked on the street by youths who thought he was Jewish. The murder of Vienna Circle leader Moritz Schlick by a deranged former student in 1936 had triggered in Godel an obsessive fear of poisoning that would never leave him. His academic position was dissolved under the Nazi regime, and in 1939, he was found fit for German military conscription. In early January 1940, Godel and his wife Adele, a former nightclub dancer 6 years his senior, whom he had met at a Viennese club called Der Nachtfalter, the Moth, in 1927, fled Vienna by an extraordinary route. Unable to take a transatlantic steamer because the British screened German citizens, they traveled through occupied Poland and the Baltic states, across Russia on the Trans-Siberian Railway, to Vladivostok, by ship to Japan, across the Pacific, arriving in San Francisco on March 4, 1940, and then by train to Princeton. At the Institute for Advanced Study, Godel formed one of the most celebrated intellectual friendships in history with Albert Einstein. Starting around 1941, they walked together daily to and from the Institute, conversing in German, Einstein rumpled in baggy pants, Godel lean and dapper in a white linen suit and matching fedora. Einstein told Oscar Morgenstern that he went to the Institute chiefly to have the privilege of walking home with Kurt Gödel. They turned to each other because they could turn to no one else. In 1949, Godel gave Einstein a birthday gift, solutions to Einstein's own field equations involving closed time-like curves, mathematical permission for time travel. The result unsettled Einstein so deeply that he began to have doubts about his own theory. Einstein's death on April 18, 1955, devastated Godel and worsened his reclusion. Gödel's mental stability deteriorated throughout his life, dominated increasingly by paranoid delusions about being poisoned. He would eat only food tasted first by Adele. He believed in ghosts. He feared refrigerator gases. Morgenstern recalled Adele describing how, in the 1930s, she had fed Godel spoonful by spoonful to bring his weight from 48 to 64 kilograms. In late 1977, Adele was hospitalized for approximately 6 months. Without her to taste his food, Godel refused to eat. He was admitted to Princeton Hospital and died sitting in a chair in his hospital room on the afternoon of January 14, 1978. He weighed 65 pounds. His death certificate stated the cause as malnutrition and inanition caused by personality disturbance. The man who proved that no self-referential system can validate itself from within died because his own self-referential system of paranoid logic became a closed loop from which he could not escape. The logician who showed that no system can prove its own consistency died because he could not prove the consistency of his own sustenance. The parallel between his mathematics and his death is so precise, it feels engineered by something cruel. Hilbert had died decades earlier, on February 14, 1943, in a Göttingen that had been gutted by the Nazis. When the Nazi education minister asked him how mathematics was going, now that it has been freed of the Jewish influence, Hilbert replied, "Mathematics in Göttingen? There is really none anymore." His funeral was attended by fewer than a dozen people. Only 2 were fellow academics. The words on his tombstone read, "Wir müssen wissen. Wir werden wissen. We must know. We will know." Carved in stone, in a city emptied of mathematicians, in a world that had proved otherwise. And if this were just a story about mathematics and the people who did it, it would already be disturbing enough. 2 men who discovered fundamental limits on human knowledge, both destroyed, one by a government that could not compute his value, one by a mind that could not verify its own inputs, the institution that could not recognize its savior, and the system that could not prove its own consistency. But the results did not stay inside mathematics. That is what you were never told. What Godel found in formal systems and what Turing found in computation has been found in physics itself. And the way it was found is worth understanding, because the way it was found matters. This is a direct, rigorous, mathematical proof that the halting problem, Turing's halting problem, the one about the abstract machine with the infinite tape, is physically encoded in the behavior of quantum materials that exist in laboratories right now. To understand why this is so devastating, you need to understand what physicists thought they were building toward: the dream of a theory of everything, a single mathematical framework that describes all physical phenomena, has been the organizing ambition of theoretical physics for the last 100 years. Einstein spent the final 3 decades of his life searching for it. String theory was supposed to deliver it. The Standard Model is an approximation of it. The assumption behind the entire enterprise is that the laws of physics are, in principle, fully describable by mathematics, that if you had enough cleverness and enough data, you could write down the equations that govern everything. What came next showed that this assumption is provably wrong. On December 10th, 2015, the journal Nature, volume 528, pages 207 through 211, published a paper by 3 physicists: Toby Cubitt at University College London, David Perez Garcia at the Universidad Complutense de Madrid, and Michael Wolff at the Technische Universität München. The paper proved something that should have been front-page news in every country on Earth. It proved that a fundamental property of physical matter is undecidable. The property is called the spectral gap. In quantum mechanics, the spectral gap is the energy difference between a material's ground state, its lowest possible energy, and its first excited state, the next energy level up. Whether this gap exists or not determines whether a material is an insulator or a conductor, how correlations between particles decay over distance, and the robustness of quantum phases of matter. This is one of the most important physical properties a quantum material can have. What Cubitt, Perez Garcia, and Wolff proved is that determining whether the spectral gap is zero or non-zero is undecidable, not hard to calculate, not beyond current computational power, undecidable, in the same sense that the halting problem is undecidable, in the same sense that Gödel sentences are undecidable. The proof works by constructing families of quantum spin lattice models, whose spectral gap depends on whether an encoded universal Turing machine halts. If the encoded machine halts, the system is gapless. If it runs forever, the system is gapped. Since the halting problem is undecidable, so is the spectral gap. And here is the part that should stop you cold. There exist physical models for which the presence or absence of a spectral gap is independent of the axioms of mathematics, not independent of current axioms, independent of any axioms anyone will ever choose. No framework will ever be sufficient. The question is unanswerable within any consistent mathematical system. Think about what this means for the dream of a theory of everything. Physicists have spent the last century searching for a single mathematical framework that describes all physical phenomena, a set of equations that captures every force, every particle, every interaction in the universe. The spectral gap result does not just make this harder, it puts a mathematical ceiling on it. There exist physical properties that no mathematical theory, no matter how complete or sophisticated, can decide. The halting problem is not confined to Turing's hypothetical tape machine. It is embedded in the energy structure of matter. You could be holding a material in your hand right now, whose spectral gap status is formally independent of the axioms of all known mathematics. Not unknown, unknowable. That is a different thing entirely, and the difference matters. Unknown means someone might figure it out eventually. Unknowable means the question lives outside the reach of any formal system, and adding new axioms does not fix the problem. It just moves it. New, undecidable questions appear. The gap regenerates exactly as Godel predicted it would in 1931. And the spectral gap paper was just the beginning. In 2020, Bausch, Cubitt, Lucia, and Perez Garcia extended the result to one-dimensional systems, published in Physical Review X. One-dimensional, not some exotic high-dimensional lattice. A chain, a line of particles, the simplest possible geometry, and undecidability is already there. In 2021, Shiraishi and Matsumoto proved in Nature Communications that whether an isolated quantum many-body system thermalizes, meaning whether it reaches thermal equilibrium, is undecidable. That is not an abstract mathematical property. Thermalization is what happens when you put an ice cube in a glass of water. Whether certain quantum systems do something analogous to that, whether they settle into equilibrium or remain in a perpetually non-equilibrium state, is a question that mathematics cannot answer. The same year, Bausch, Cubitt, and Watson showed in Nature Communications that phase diagrams, the maps physicists use to predict how materials behave at different temperatures and pressures, are uncomputable. The tools that materials scientists use every day to understand the behavior of matter have formal limits that cannot be exceeded. And as early as 2012, Isert, Muller, and Gogolin had demonstrated in Physical Review letters that determining whether certain measurement outcome sequences can occur in quantum systems is undecidable. They called it a genuine quantum property with no classical analog. The universe does not merely contain undecidable mathematical propositions. It contains undecidable physical events, things that will or will not happen, and no mathematical theory can determine which. And then there is Yuji Tachikawa's result, published in the International Journal of Theoretical Physics in 2023. Tachikawa showed that whether a two-dimensional supersymmetric field theory breaks its supersymmetry is undecidable, and he identified a specific theory that breaks supersymmetry if and only if ZFC set theory, the standard axiom system for mathematics, is consistent. By Gödel's second incompleteness theorem, the consistency of ZFC can never be proved from within ZFC, which means the physical behavior of this particular quantum field theory is logically tied to a question that mathematics itself has proved unanswerable. The physics and the mathematics are knotted together in a way that admits no resolution. A major review paper by Perales Ezeiza, Cubitt, Gu, Perez Garcia, and Wolf, published in Physics Reports in 2025, surveys the entire landscape of undecidability in physics. And in the same year, Faisal, Krauss, and their collaborators argued that a wholly algorithmic theory of everything is impossible. Their conclusion was blunt. Quantum gravity cannot be both consistent and complete, and certain facets of reality will remain computationally undecidable. Stephen Wolfram arrived at a related conclusion from a different direction. Through decades of studying cellular automata, those simple grids of cells that evolve according to local rules, Wolfram developed the concept of computational irreducibility. A process is computationally irreducible if there exists no shortcut to predicting its outcome other than running the computation step by step. You cannot fast forward. You cannot write an equation that leaps to the answer. You have to watch it unfold. His principle of computational equivalence, articulated in his 2002 book, A New Kind of Science, states that almost any system whose behavior is not obviously simple is computationally equivalent to a universal Turing machine. If this is true, then computational irreducibility is not rare. It is the default condition of complex systems, and it directly entails undecidability. Traditional theoretical physics succeeded precisely because it found computationally reducible aspects of reality. Newton's equations let you predict where a planet will be in 1,000 years without simulating every second of its orbit. Maxwell's equations let you calculate the behavior of electromagnetic fields without tracking every photon. But Wolfram's argument, supported by his 1985 paper Undecidability and Intractability in Theoretical Physics in Physical Review Letters, is that this success was the exception, not the rule. Some physical behaviors can never be predicted by any theory simpler than the system itself. The universe does its own computation, and there is no shortcut. You were taught in school that physics is the science of finding equations that describe nature. That given enough cleverness and enough data, we could eventually write down the rules that govern everything. What these papers say is that this belief is wrong in a provable mathematical sense. And the proof is not controversial or speculative. It is published in Nature, in Physical Review X, in Nature Communications. It has been checked and extended by independent groups for a decade. It is settled. And yet, how many times has a popular science channel explained this to you? How many times has a physicist on a podcast mentioned that the spectral gap of a quantum material is formally undecidable? How many times has anyone with a platform said the words, "The halting problem is embedded in the physics of matter," to an audience that was not already composed of specialists? This was confirmed in 2015. It should have changed how we talk about the limits of science. It did not. Now, there is an important misconception to correct here. Roger Penrose, the Nobel Prize-winning physicist, took the connection between Gödel's theorems and physics in a different direction, one that gets a lot of attention, but is, in the judgment of the overwhelming majority of experts, wrong. In The Emperor's New Mind in 1989 and Shadows of the Mind in 1994, building on philosopher John Lucas's 1961 argument, Penrose claimed that human mathematicians can see the truth of Gödel's sentences that no formal system can prove. Therefore, he argued, human understanding must involve non-computable processes. He proposed that consciousness arises from quantum gravity effects in brain microtubules. The argument fails. Hilary Putnam pointed out that humans frequently err in mathematical judgments. David Chalmers identified the fatal weakness. We cannot know that we are sound. If our minds are consistent formal systems, we cannot determine our own Gödel sentences. And if our minds are not consistent, meaning they sometimes produce contradictions, which they obviously do, then the Gödelian argument does not apply to us at all. Turing himself had preempted the objection in 1950, noting that a human could beat any particular machine via the incompleteness theorem, but it would be impossible to triumph over all machines simultaneously. The claim that Gödel's theorems give humans something machines can never have is not supported by the mathematics. What the mathematics actually supports is something more uncomfortable. We may be no less trapped than our machines. If human minds are formal systems, they inherit the same limits. If they are not formal systems, we have no idea what they are or how they work. Either way, the Gödelian escape hatch does not open. Douglas Hofstadter brought some of these ideas to a mass audience in his 1979 book Godel, Escher, Bach, An Eternal Golden Braid, which won the Pulitzer Prize for General Nonfiction in 1980. It remains one of the most influential popular science books ever written. But even Hofstadter focused primarily on the self-reference and the beauty of the results. The darker implication that the limits are not just inside our theories but inside reality itself would not be confirmed for another 35 years. Gregory Chaitin, born June 25, 1947, gave incompleteness yet another dimension through his work on algorithmic information theory. His most profound contribution is the omega number, introduced in a definitive 1975 paper in the Journal of the Axiom. Omega is the probability that a randomly constructed program will halt. It is a specific, well-defined real number between 0 and 1, but it is uncomputable. No algorithm can produce its digits, and for any consistent axiom system, there exists a point beyond which no further digit of omega can ever be determined. Godel showed that some truths are unprovable. Chaitin showed that the unprovable truths are overwhelmingly the norm, not rare pathological exceptions. As Chaitin put it, Godel showed incompleteness is real, but omega shows the situation is far worse. Mathematical truth contains irreducible randomness. That is where this leaves you. Hilbert stood in Paris in 1900 and said we will know. Godel sat in a conference room in Königsberg in 1930 and proved that we will not. Turing lay in a meadow in Cambridge in 1935 and proved that no machine will ever bridge the gap. And in 2015, 2020, 2023, 2025, paper after paper after paper confirmed that the gap is not inside our theories. It is inside reality. The universe contains physical systems whose properties are not merely unknown, but unknowable, independent of any axioms we might adopt, independent of any mathematical framework we might invent, independent of any computer we might build, any theory we might write down, any intelligence, human or artificial, that might someday attempt the problem. The halting problem is not a metaphor for the limits of physics. It is a theorem about the limits of physics. Turing's abstract tape machine and the energy structure of a quantum lattice are connected by the same thread of undecidability, and that thread cannot be cut. There is something almost unbearable about the symmetry of what happened to the people involved. The man who proved that formal systems cannot be complete was found dead in a chair in Princeton Hospital, weighing 29 kilograms, because the system inside his own mind had become a closed loop from which no exit was possible. He could not trust his food. He could not verify his inputs. The external validation mechanism, his wife Adele, was removed by illness, and without it, the system collapsed. It is Gödel's second incompleteness theorem, made flesh, a system that cannot prove its own consistency, running to its inevitable conclusion. The man who proved that computation cannot decide all questions was found dead in his bed in Wilmslow, with an apple beside him that nobody thought to test, because the country whose survival he had ensured could not compute the value of a man who loved other men. He had saved 14 million lives and was repaid with chemical castration. He had invented the conceptual foundation of every computer on Earth, and the state broke him for who he slept with. The machines he imagined would go on to reshape civilization. He was not alive to see it, and the mathematician who started it all, who stood in Paris and promised that we would know, died in a Göttingen, emptied of his colleagues, by a regime that had decided some questions about who deserved to live, had very simple answers. Indeed, his funeral was attended by fewer than a dozen people. His tombstone still says, "We must know, we will know." Nobody had the heart to correct it. The calculations have been checked. The theorems have been proved. The physical results have been replicated and extended for a decade, and the conclusion is the same at every level, from Gödel's arithmetic to Turing's machines to the quantum spin lattices in condensed matter labs. There are questions that cannot be answered, not because we are not smart enough, not because we have not worked long enough, because the structure of reality includes the impossibility of its own complete description. And the people who discovered this, every single one of them, were punished for it, by governments, by illness, by indifference, by the very systems they had given their lives to understand. The universe is richer than any description of it can be, and we may be no less trapped than the machines we build to describe it. Gödel knew this. Turing knew this. And what it means for reality is something that even now, almost nobody is willing to say out loud.